Hello, everyone. My name is Xiao. I'm a graduated PhD student at Duke University and now an internet measurement researcher at Southern Eyes. Today, we are going to introduce our measurement research on the regional IP Anycast network. This is a joint research project with Nanjing University, Duke University, and Old Dominion University. First, let's take a look at the Anycast inefficiency. As shown in lots of previous research, even we have methods to optimize the performance of IP Anycast, some probes round-trip time can still be very long. For those probes have very long round-trip time, it's usually caused by Anycast plus inflation, which lead them to a further away site. In this example, CRUNIP server have multiple different sites deployed around the world, but the probe in Singapore was routed to IP Anycast sites in Los Angeles, rather than the closer sites deployed in the same country. Therefore, can we optimize Anycast performance by restricting the sites client could reach? In this project, we found two large CDN providers, Agile and Improva, already implement such kind of optimization. To lead the clients to nearby sites, we can first announce a prefix from several sites which is close to the clients, then give that Anycast prefix to the client by utilizing DNS. This figure provided by Improva shows the paradigm. The color dots stand for the sites that announce different prefixes, and the dashed shape outlines the clients should get that prefix. To show the effectiveness of a regional IP Anycast, we follow a three-step pipeline. First, we conduct the measurement to show two things: client partition, which will rewind how the CDN provider return different prefix to different clients, and the CDN site partition, which shows how the CDN provider announce different prefixes with its available Anycast sites. With above information, we evaluate the performance benefits of the regional IP Anycast and also compare with its global counterpart. In the end, to explain the reason of the performance benefits, we also analyze the AS relationship and routing information along those trace routes, and we found two typical reasons. To analyze the performance, we first need to figure out the region and how the region is departing. To do that, we can just use DNS query provided by REP as probes. We issue DNS query to the domain hosted by Agile and Improva from all available REP as probes, and the different A record received by each probe will show the result. The red graph shows the client partition of Agile 3. Each dot stands for different locations of different probes, and different color shows different IP addresses each probe received. Have the client the partition is not enough. We still have to find out which Anycast sites are used to announce those prefixes. In similar research before, we can use DNS chaos query to find out the Anycast sites current probe reached to. But CDN server usually do not support DNS chaos query. Therefore, in this work, we depend on trace route issued from the probe to the hostname to figure out the CDN sites partition. In this method, we can get trace route from the probe to the Anycast site it get to. We depend on penultimate hop's information to locate the site, because the penultimate hop is usually the edge router of that site. We will utilize multiple different sources, including the reverse DNS entry of the penultimate hop, officially published documents, closest sites probes which also traverse through the same penultimate hop, and also different IP-geo databases for that hop. We use three steps to locate the reached IP Anycast sites of current trace route. First, we find out penultimate hop's reverse DNS entry. The two CDN providers provide the naming schema of their edge router in their official documents. For example, the AMB in this case means the second edge router deployed in Amsterdam. Besides these edge routers, we still have some other penultimate hops that cannot be resolved. This usually happens when the penultimate hop belongs to its peering ASs or XPs. In this case, we cross-check the nearest probe's location, which going through the same penultimate hop with the potential location from those three different IP-geo databases. If one of the IP-geo databases result falls into the result of the nearby probe's round-trip time range, we use the IP-geo's result. If above two steps still cannot resolve the site's location, we use the country-level IP-geo result. When there are only one site deployed in the country of the IP-geo's result, we use that location. The group stick bar chart shows the composition of resolution result of the penultimate hop and corresponding trace route. In the ideal 3 case, over 66% of the penultimate hop can be located to a site with reverse DNS entry, and that's corresponding to over 95% of the valid trace route we got. With this result, we can also find out enable sites used by different prefixes. After mapping out those host name hosted by 2 different providers, we can find out 3 different partition schemas: Agile 3, Agile 4, and IM6. Compared with Agile 3, Agile 4 have 4 more sites enabled in South America, and those 4 new sites have its own prefix. We can also notice that we can map only half of the published sites in Agile's documents, but we can map out almost all of Improva's published sites. In evaluation, to mitigate the bias, we have 2 methods. First, we group the RevS probes into AS geo groups to balance the probes distribution density problem. And we also conduct the performance comparison within each different regions. We have 4 regions in total. We first showed benefits brought by finer grain partition by comparing Agile 4 with Agile 3. As we can see in the red graph, for Agile 3 and Agile 4, the probe groups in EPIC, MA, and NA do not bear observable differences in the round-trip time distribution. But for Latin America, the 80th percentile round-trip time reduced from 132 milliseconds to 76 milliseconds due to the new prefix and 4 more enabled sites in that region, so that the probe groups in that region can be routed to local sites. This showed difference tiers and the package provided by CDN providers. The finer partition can achieve better performance by limiting the client's reachability. But how about performance compared with global Anycast? In this part, we compare the performance of Improva 6 with its global counterpart, Improva NS. Since they share almost the same set of Anycast sites, even IM6 and IMNS share almost same set of Anycast sites, they can be announced differently at different sites. Therefore, we only select the trace block that went through the same set of sites and through overlapping ASs and also XPs. The comparison result shows 2 regions, APAC and AMEC, do not have too much difference, but in Latin America, regional IP Anycast performance is worse because it's impacted by DNS mapping error, which means the probe in this region tend to get wrong regional IP Anycast prefix which belong to the other regions. To conduct apple-to-apple comparison, we utilize Tango testbed. It have 12 different sites all over the world, and we split them into 5 different partitions with latency-based method and announce them indifferently. In the end, we use the country-level mapping provided by Amazon Route 53. The results show significant better performance in the regional IP Anycast. With the evaluation result, we show finer partition and also regional Anycast can bring great performance benefits. But what is the reason? In this part, we analyze the trace route which have 5 millisecond better round-trip time in the regional Anycast and find 2 typical root causes. After getting the trace route, we get the ASXP path of the regional and also global trace. For the first case, we find out regional IP Anycast can optimize the performance by overwriting AS relationship preferences. In the first example, the Washington DC probe get to Ashburn Anycast sites with only 2 millisecond round-trip time, but the global IP Anycast path goes to Singapore site with over 200 millisecond round-trip time. Although the Ashburn site announced the global IP Anycast prefix at the same time, the global IP Anycast prefix from Singapore came to Zayo network from a customer peer. Therefore, Zayo will select this one. We also found regional IP Anycast can optimize the performance by overwriting peering type preference. To sum up our contribution, in this work, we study Agile and Improva's deployment and also performance. And we also compare the regional Anycast prefix with its counter global part. We also showed that regional IP Anycast can effectively mitigate the worst case catchment efficiency which happened in the global IP Anycast one. And also in the end, we test on the Tango testbed with 12 different sites around the world, and we announced those 2 different deployment globally and without the configuration difference.